Logistic regression explained. Every observation that we encounter will have a probability of being what we call the success class, or one, or yes, or whatever, however we're labeling it, and a corresponding probability of failure. And what we'd like to do, create a function. We want a way to separate things that are likely to be success from things that are likely to be failure. Attempt at this, and so odds are the probability of success divided by probability of failure. We're assuming that everything is either a success or a failure, so we don't need to write probability of failure. What could we write instead? We could write 1 minus the probability of success. I don't want to write probability of success over and over again, so let's make the notational convention. So I'm just going to write the letter P for the probability of success. And so what I have now is I have a function, odds, which takes in a probability of success, which can be from 0 to 1, and puts out a real number. This is given by odds of P is equal to P over 1 minus P. This could be as low as 0, but approaching infinity, if P is close to 1, then the denominator would be close to 0, right? It's a 0. What would the odds be? And so it has the 0, 0 business. What about if the probability of success is truly 0.5? It's just a coin flip. What would odds be? 1? And what about if P is actually 1? Odds would be infinity, or you could say the limit. More rigorously, we would say the limit as P approaches 1 from the left of odds is equal to infinity. But we have a function that looks like this. And I mean, like, that's not going to work. Instead is we're going to take this function that only goes from 0 to 1, and we're going to transform it. And instead of looking at odds, we're going to look at the logarithm of odds. So let's look at log odds. Why does this work better? This works better because now, instead of having this weird asymmetry, if I take the log, if P is approaching 0 from above, and the log of the odds approaches negative infinity. If P is equal to 0.5, the log of the odds equal to log of 1, which is 0. And if P approaches 1 from below, the log of odds approaches positive infinity. And this is somehow feels a lot better. Why? The negative class was squeezed into this corner here from 0 to 1. And then the positive class was like all this space. 0 is exactly the dividing line. So if I have my odds, if I have my event being equally likely or unlikely, the log odds, if P is equal to 0.5, that's like a coin flip. Well, the log odds are 0 then, and that makes sense, that you would want kind of a neutral outcome if it's exactly likely or unlikely. And the more likely P becomes to be positive, the larger it becomes, approaching positive infinity. As this event becomes more likely, this log odds can grow without bound in the positive direction. And as it becomes less likely, as the probability goes towards 0, I'm seeing log odds are approaching negative infinity. So now what we want the data set to be linearly separable, which means we're going to be looking for a function where our output is something that can separate this. It's going to be something of the form. Let's say for a minute that we're only dealing with a linear function. So we're separating points in the plane. And so this line would have the form a0 plus a1 times x0, x1 rather, plus a2 times x2. And I'm going to use x1 for my x-axis and x2 for my y-axis. Well, now I'm going to say that the output of this should correspond to the log odds. Why? Well, let's look at what happens. Let's look first at what happens if we have a point that's actually on the line. If we have a point that's actually on this line, we would want the output to be 0. If we have a point that's above the line, we want the output to be positive. And if we have a point that's below the line, we want the output to be negative. So we're going to make this line, pick a point that's exactly on the line and you plug it in, the output will be 0. So this line will have the form a0 plus a1x plus a1x1 plus a2x2 is equal to 0. And if you plug in something above the line into this function, it will be positive. The line will be negative. Want this to be positive if it's above the line, negative if it's below the line, zero if it's up on the line. So what we actually want is the line probability being exactly 50% where we can't classify it. So this output that we're going to look at is the log odds. So we're going to look at the log of P over 1 minus P being equal to this equation of this line. Solve for P. We have the log P over 1 minus P is equal to this equation of this linear function. Mathematician says log, they mean natural log. Log without a base for the rest of your life, unless you're an engineer, is log base e. All right, so I can cancel this by raising log of P over 1 minus P is equal to e to the a0 plus a1 x1 plus a2 x2. And now I have P over 1 minus P is equal to e to the a0 plus a1 x1 plus a2 x2. Yeah, this is not the most fun thing I've ever done, but it's all right. Do you have any suggestions on what we can do? You're trying to solve for no. Thank you. And now this is an unknown. We're just trying to solve for P. I have P equals this E expression, e to the a0 plus a1 x1 plus a2 x2 minus P times e to the a0 plus a1 x1 plus a2 x2. Add this thing to both sides. So this is P plus P times e to the a0 plus a1 x1 plus a2 x2 equals this e to the a0 plus a1 x1 plus a2 x2. Do you agree? And then we're going to have factor out of P. So we have 1 plus e to the a0 plus a1 x1 plus a2 x2 equal to e to the a0 plus a1 x1 plus a2 x2. Do you agree? Okay, what should I do now? Should divide through by 1 plus e to the a0 plus a1 x1 plus a2 x2. And I can also divide this side by that. And then I'm going to take a moment because that's a lot to write. So I'm going to cancel this, and now I have P is equal to e to the a0, a1 x1 plus a2 x2 all over 1 plus e to the a0 plus a1 x1 plus a2 x. But I could multiply this through by the multiplicative inverse of which would be e to the negative a0 plus a1 x1 plus a2 x2. And as long as I do the same thing to top and bottom, that is totally legal. Do you agree? Now, when you combine these add to give you e to the 0 on top, which means that now I just have a 1 in my numerator. And then when I distribute this through, I get this expression times 1 plus this expression times its multiplicative inverse. So it becomes this thing. After doing all this work, we now want to write the 1 in front on the denominator. So the way you'll see this when you actually look at it is P equals 1 over 1 plus e to the negative a0 plus a1 x1 plus a2 x2. And this is called a logistic function, which is why this is called logistic regression. Then when you plug in the x and y coordinates, this will give you the probability of success based on your x and y coordinates. This is based on 3 parameters, a0, a1, and a2. And so in the real, when you actually have one of these, you won't have a0, a1, and a2, you will have numbers. Just like when you're in calculus, you have y equals mx plus b as the general form of a line, but then a specific line is something like y equals 2x plus 5, right? So we have the general form of a logistic function in 2 input variables, but a specific version would be where we actually had numbers plugged in. What we actually have to do is figure out what are the right numbers to make this be the right line, so that the things above the line are, the further up you get above the line, the higher probability you have of being in the 1 class or the success class. And so that in the below the line, you have a lower probability. And we're actually going to punt on that question of how we determine the values, because that is an optimization problem in multiple variables, which is something we will talk about way later. One more thing. Am I restricted to 2 variables on this process? No. Could I generalize this to any number of